Scientists and physicists have always been fascinated by the universe and the phenomena they unraveled from it. But one thing remains that keeps them seated at their research table for years, and that is antimatter. When scientists previously talked about antimatter, they had very little to discuss. This is because antimatter is one of the strangest things in our universe. However, a recent discovery was made by scientists, and it is not only set to change our perspective, but also explain the mystery behind antimatter. What did scientists find out? Is antimatter capable of destroying our universe? Join us as we explore the unsolved mystery behind antimatter. Think about matter, then imagine if the matter had a twin but with different properties and charges. Yes, that's antimatter. Although it's been a widespread topic of science fiction stories for several decades, antimatter is real and deeply rooted in modern scientific theory. The existence of antimatter was confirmed in 1995 by a team of scientists at the University of California, Berkeley, which won them the Nobel Prize 4 years later. When antimatter is exposed to ordinary matter, it destroys both of them. Though this destruction seems mysterious, it has its own benefits attached. When matter and antimatter collide, it releases energy powerful enough to power a light bulb or even a city. While this remains a mystery, scientists and physicists are still researching ways to harness that energy, but all attempts have been unsuccessful. That makes it another mystery, further proving why antimatter is one of the mysteries of the world of science. So what exactly is antimatter, and why has it troubled the world of science for generations? Antimatter refers to particles similar to the ordinary matter we're familiar with. Such antiparticles have the same mass as their normal particle doppelganger, but remain their opposites in some parts. To give you an insight, a positive electron, also known as a positron, has the same mass as an ordinary electron, but a positive charge opposite the electron's regular electric charge. Antimatter was initially predicted by British physicist Paul Dirac in 1928 when he tried to combine quantum mechanics, which explains subatomic particles, and Albert Einstein's theory of relativity. Dirac was examining solutions to an equation that best describes the movement of an electron moving near the speed of light. Now, just as the equation x raised to the power of 2 equals 4 can provide two possible solutions, x equals 2 or x equals minus 2, Dirac's equations could have two solutions as well, one for an electron with negative energy and one for an electron with positive energy, according to the European Organization for Nuclear Research. At first, Dirac didn't want to share his findings with the public, but eventually he accepted them and postulated that every particle in the universe should have a mirror image particle that acted like it but had an opposite charge. A few years later, positrons were found by American California Institute of Technology physicist Carl Anderson. On the 2nd of August 1932, Caltech physicist Carl Anderson was the first to spot the first particle of antimatter. Discovering the positron was not expected, as Anderson had not intended to search for antimatter. He had constructed a cloud chamber to find the composition of cosmic rays and high-energy particles that fell from space. Anderson's instrument also comprised a magnet, which allowed him to determine whether particles passing through were either positively or negatively charged. It also had a lead plate that slowed the particles down. He took several photographs of the tracks taken by cosmic ray particles, but he was held off by one particular way made by one of the particles. This particle's trajectory curve gave off evidence that the particle was positively charged, yet far less massive than a proton. An editor at the journal Physical Review suggested the positron since the particle looked like a positively charged electron. Anderson didn't realize until later that the positron was similar to the electron except for the opposite charge, a theory that Paul Dirac had predicted the existence of such a particle in 1931. This discovery won Dirac and Anderson the Nobel Prize in Physics. Dirac won in 1933, Anderson in 1936. Antimatter is occasionally produced in particle accelerators and also occurs through the collision of high-energy particles in the Earth's atmosphere. However, this isn't enough to study it, as its mystery is hidden deep in its marked absence. As far as scientists can tell, the universe around us is mainly made of matter with no antimatter. This baffles scientists and keeps forcing them to restudy theories surrounding the universe's inception, also known as the Big Bang. The Big Bang Theory first surfaced in the early 20th century. It was developed to explain the observations made by Lemaitre, Slipher, and Hubble, saying that visible galaxies were moving away from Earth in all directions. That leaves us with two interpretations. Either the world is at the center of a cosmic explosion of galaxies, or space in its entirety is expanding everywhere. Well, the explanation about space expanding everywhere seemed more justifiable and has been chosen as the common consent in science ever since. The effect is like testing the capacity of a rubber band's length or inflating a balloon. Two marks on the rubber's surface will move apart, not due to the relative motion of the dots along the rubber, but because the space in which they exist is stretching apart. Naturally, upon observing the continual expansion of space, scientists and even the public in general cannot help but imagine how things looked in the universe millions or billions of years ago. Before the universe was born, things must have been denser, hotter, and much closer. As the Big Bang Theory explains, all of matter, space, and time suddenly exploded out from that point, birthing the universe and expanding as it cooled down. Quantum fluctuations of photons in this plasma continually created pairs of electrons and positrons, particles and antiparticles. Some of these particles were developed and destroyed almost immediately, but as the plasma kept expanding and cooling down, some particles and antiparticles were also created but did not annihilate. These particles are what eventually amassed to form atoms, stars, planets, and everything we see around us in our universe today. But what about the antiparticles? Where did they go, or what did they form into? We know the processes that started all the matter we see. We are aware that an equal amount of antimatter must have been created alongside. But where are they? This remains one of the most central unanswered questions in modern cosmology, and many scientists are working hard to solve the puzzle. In a bid to find a solution to this mystery, scientists came together to create antimatter particles with the use of ultra-high-speed collisions at colossal particle accelerators. One such particle accelerator is the Large Hadron Collider located outside Geneva and operated by the European Organization for Nuclear Research. Their experiments have covered a range of tests, one of which led scientists at CERN to create anti-hydrogen, the antimatter twin of hydrogen. The most complex antimatter element produced to date is anti-helium, the counterpart to helium. Although antimatter is produced in several experiments at CERN, the antiparticles produced cannot be trapped because of their very high energy. This high energy makes them destroy themselves harmlessly in the detectors, and even when made, they are produced in very tiny quantities. It's small to the extent that even if CERN uses its accelerators only to make antimatter, it can't produce more than about 1/1000th of a gram per year. This means producing 1 gram of antimatter would take approximately 1 billion years. Since the Large Hadron Collider was invented, the entire amount of antimatter produced in the history of CERN is less than 10 nanograms, containing only enough energy to power a 60-watt light bulb for 4 hours. Also, another problem scientists face with these experiments is that the efficiency of antimatter production and storage is very low. About 1 billion times more energy is needed to make antimatter than is eventually contained in its mass. Using the formula E equals mc squared, we can see that 1 gram of antimatter contains 0.001 kilograms times 300 million meters per second squared, which equals 90,000 gigajoules or 25 million kilowatt hours. This means that with its low production efficiency, it would require 25 million billion kilowatt hours to produce 1 single gram. And that's basically too much for the electricity output in our generation, because even at a discount price for electric power, this would cost more than €1 billion to run. But one peculiar mystery about antimatter that baffles scientists and returns them to the drawing board is that in the beginning, matter and antimatter coexisted, but now we can only observe matter. How is this so? Despite being one of the defining mysteries of physics, physicists and scientists came up with some theories that could solve this age-old mystery. Most of these theories postulated by scientists and physicists involve the existence of extra particles beyond the recognized species in the universe. However, these findings made by scientists all turn towards one solution, but the data falls short of a definitive discovery. Still, figuring out this mystery would most likely teach us more than just why we exist in a universe of matter. It could explain hidden details from the earliest era of the cosmos, or even link scientists to the invisible dark matter that confounds science. Most theories about how matter became more than antimatter fall into two main categories. The first category, called electroweak baryogenesis, postulates different versions of the Higgs boson. The Higgs boson is the particle related to how every other thing possesses mass. If these Higgs relatives genuinely existed, they could have helped set off a sudden phase transition related to the shift when water goes from liquid to gas. It could have happened early in the universe, which might have caused slightly more matter than antimatter to be in space. When antimatter and matter come in contact, most things in the young universe would have been annihilated, leaving just a tiny residue of matter to make the galaxies, stars, and planets around us. The other leading theory, named leptogenesis, branches instead from neutrinos. These particles are lighter than quarks, and they pass through the cosmos in a celestial way, barely stopping to interact with anything. According to this outline, in addition to the regular neutrinos we know of, there are very heavy neutrinos that are so enormous that they could have been formed only from the immense temperatures and energies present just after the Big Bang, when the universe was very dense and hot. When these particles naturally broke down into smaller and stable species, the thinking goes they might have created slightly more matter than antimatter byproducts, leading to the positioning we see today. However, a recent announcement by scientists at the Tokai to Kamioka experiment in Japan gives optimistic signs for the leptogenesis concept. The experiment observes neutrinos as they journey through 300 kilometers underground and transform between three types or flavors, a unique ability exhibited by neutrinos called oscillation. The T2K researchers found more oscillations in neutrinos than in antineutrinos, proposing the two do not just act as mirror images of each other but act in different manners. Such contrast between a particle and its antimatter counterpart is termed CP violation. It is a bona fide clue in the quest to know how matter outran antimatter after the universe was born, although the team of scientists does not call this a discovery yet. The experiment has now cancelled the possibility that neutrinos have zero CP violation with 95% confidence. It gives clues that the particles might show the maximum possible amount of CP violation permitted. Still, more data and maybe future experiments will be required to accurately measure just how much neutrinos and antineutrinos vary. Yet, even if physicists make a definitive discovery of CP violation in neutrinos, they will not have totally found an answer to the cosmic antimatter question. According to Seda Ipek, a theoretical physicist at the University of California, Irvine, such a finding would be necessary but not enough to prove leptogenesis. Another necessity of the theory is that neutrinos and antineutrinos turn out to be the same thing. How is that seeming contradiction possible? Matter and antimatter are thought to be alike except for a reversed electrical charge. Neutrinos having no charge could be both simultaneously. If this probability is the case, it could also analyze why neutrinos are so light, bringing it to maybe less than 1/6 millionth of the mass of the electron. If neutrinos and antineutrinos are the same, they might gain mass, but not by interrelating with the Higgs field as most particles do, but by another process called the seesaw mechanism. Their tiny masses would be reversely equivalent to those of the heavy neutrinos that woke up in the early universe. When one is up, the other is down, like a seesaw, Ipek said. Jessica Turner, a theoretical physicist at the Fermi National Accelerator Laboratory, also commented. She said, "Leptogenesis is a very elegant way of explaining things. Firstly, you answer why there's more matter than antimatter, and second, you explain why neutrinos have such small masses." Proof that neutrinos are their antimatter equals could have been derived from experiments looking for a theorized reaction called neutrinoless double beta decay, which could only occur if neutrinos were able to destroy themselves as matter and antimatter do on contact. Even this discovery, though, would not wholly show leptogenesis occurred. If you measure the possible CP violation we can see, and if you observed the neutrinos were their own antiparticles, we would say that's circumstantial evidence, not direct evidence, Turner concluded. The other theoretical option on deck, electroweak baryogenesis, could be easier to look into, physicists say. While the heavy neutrinos creation involved in leptogenesis could be beyond the capabilities of particle accelerators, the extra Higgs boson predicted by this theory might just become spotted at the Large Hadron Collider, says Marcella Carina, head of Fermilab's Theoretical Physics Department. Even if the machine does not produce them directly, these Higgs relatives could delicately but detectably relate with the traditional Higgs boson it makes. Electroweak baryogenesis also needs more CP violation in the universe, but not categorically in neutrinos. As a matter of fact, CP violation has already been found in quarks, though in such puny amounts that it does not explain the matter-antimatter imbalance. One place this theory's missing CP violation might be kept secret is the so-called dark sector, which is the realm of the invisible dark matter that is believed to make up most of the matter in space. Maybe dark matter and antimatter behave differently, and this dissimilarity can elucidate our universe as we know it. My line of work has been trying to connect the matter-antimatter imbalance in the universe to the idea that we know we need something we haven't seen so far in order to explain dark matter, Carina concluded. Proof for electroweak baryogenesis could show itself not just by finding extra Higgs particles, but also through the multiple experiments hunting for the dark sector and dark matter. Furthermore, if a cosmological phase transition occurred shortly after the Big Bang, as the theory suggests, it might have created gravitational waves that future experiments could discover. One such experiment is the Laser Interferometer Space Antenna, a space-based gravitational wave detector due to begin in the 2030s. In the long run, though, the universe could amaze us. Maybe neither leptogenesis nor electroweak baryogenesis happened. Those are not the only two options, as the theory realm is very vast, Ipek says. She recently worked on a model featuring CP violation in the strong interaction of the quarks in protons and neutrons. For example, theorists are checking into many other plans as well. I think we need to let ourselves scout all possibilities, Turner says. Nature unravels as it does. We can't control that. We just try our best to understand it, she concluded. Concurrently, a clear-cut measurement of CP violation in neutrinos at least is within sight. Future projects such as the Deep Underground Neutrino Experiment and T2K's successor Hyper Kamiokande should have the sensitivity required for accurate accounting. Also, since the Large Hadron Collider has established that putting matter and antimatter together creates energy, scientists and engineers have speculated that antimatter-powered spacecraft might be an excellent way to explore other galaxies. The National Aeronautics and Space Administration has examined the chances of using antimatter-driven vehicles to fly to Mars, but the idea does have some disadvantages. For one, it's costly to operate. A rough estimate to produce the 10 milligrams of positrons needed for a human Mars mission is about $250 million, using technology that is currently under development. Gerald Smith of Positronics Research LLC in Santa Fe, New Mexico, said in an article for NASA. That cost might seem high, but it still required around $10,000 per pound to transport something into orbit, so an enormous spaceship, including its human crew, would also be expensive to launch. More recently, NASA researchers have considered utilizing the energy created by matter-antimatter collisions to send a probe to the nearest star system, Alpha Centauri. The power in the collisions would permit the vehicle to speed up to 10% of the speed of light and then slow itself enough to observe Alpha Centauri, potentially for decades. Do you think antimatter would be able to achieve all these feats? Let us know your thoughts in the comments section below.